Hello, everybody. This is Dr. Ekstrom, and this is video 5, number 5 of the 7 video lectures associated with our November 1 workshop on creating content-based digital games on the structure of energy of matter. And the last 2 videos have focused on chemical bonds. Chemical bonds formed by ionic compounds, and the last one, chemical bonds formed in covalent compounds. Well, now we're going to try to link some of this back to what we discussed about mixtures in the earlier lecture in different phases of compounds by looking at how molecules and atoms of different substances can interact together. So we know, your students know, that the 3 main phases that normally occur are gases, liquids, and solids. And there are large differences in densities. Gases have very low densities, they are compressible, and they'll naturally fill whatever container you put them in. Whereas solids are high density, they very, very slightly compressible, and they're rigid, and they'll keep their shape. And of course, liquids are in between. And if we ask, really, what determines the phase that a particular substance adopts, and it all comes back to its energy content. And, exactly, okay, so will its energy content determine whether it's a gas, liquid, or solid at room temperature, higher or lower temperatures? It all has to do with how much the molecules or atoms or ions in the compound interact with one another, how strongly they interact with one another, how strongly they interact with other substances. And so if we were to relate a substance's phase and how they connect together with a function of temperature. So as we add energy or take energy away, we create what we would call either a heating curve or a cooling curve, depending on what direction you're going. And naturally, if you start at low temperature, if you go to a low enough temperature, you'll start it with a compound in the solid phase. And as you heat it, it'll eventually reach a point where it converts to a liquid. And of course, we call that process melting. And if we keep heating, then eventually that liquid will be converted to the gas phase. And of course, that process is called boiling or vaporization. And we can go in the opposite direction as well. Well, the interesting thing that we find is that when we are in the phase transition region, so when a solid is melting or a liquid is boiling, during that transition process, you can add heat, but nothing happens with the temperature. There's actually energy associated with that phase transition. So, for instance, if we start out with ice and heat the ice to melt it, when that ice reaches 0 degrees, that temperature will not change during the melting process. As it melts, the temperature stays constant. And then once it's all melted, then as we continue to add heat, the temperature of the resulting liquid water will increase. But then when we get to the boiling point and the water starts to boil, there at that point, its temperature will remain constant until the water is all boiled off. And so it's important to know that the phase transitions themselves will either absorb heat or release heat. And there's a good, well, it's kind of corny, but it's still a good video that I'll show during the workshop that kind of summarizes this in 3 minutes or less. So, at a molecular level, what's happening? So again, if we start with a solid, as energy is added, what happens is the motions of the molecules or atoms increase. Basically, in solids, atoms do move, but they basically are very small vibrations. The atoms are locked into positions if we have a crystalline solid, but they'll still vibrate. And as the solid is warm, that vibration becomes greater and greater until eventually the solid melts and those atoms or molecules achieve a greater degree of motion we call fluidity. Now, in a liquid, molecules can flow past each other, over each other, with much less resistance. However, when we reach the boiling point and the liquid particles turn into gas particles. These gas particles have high amounts of energy, and they travel at very high velocities and interact with each other to a much smaller degree than what liquid molecules or liquid phase molecules or atoms do. So these phase changes, remember, are simply physical. There are no chemical bonds that are broken. So ice, liquid water, and steam all are composed of water molecules. Nothing's happened with the water molecules. It's just that they all contain different energy contents. Of course, the ice has the least energy content, and the gas phase or steam phase has the greatest energy content. So the molecules remain intact, and what's changing, the different amounts of energy cause changes. Well, they don't cause changes really in the forces among molecules, but these different energies will result in either greater interaction or less interaction between molecules, depending on the molecule's energy content and the degree, the strength of the interactions between different molecules. So forces that occur between different molecules we call intermolecular forces. Now, chemical bonds are examples of intramolecular forces. Intermolecular forces are much weaker, but they can determine whether a compound is in the solid phase, liquid phase, or gas phase. So here in our water, in the cartoon here, we have water molecules. The OH bonds are very, very strong compared to the intermolecular forces between, here we're showing between the oxygen atom and one water molecule and the hydrogen atom and a second water molecule. That type of interaction we'll see is called hydrogen bonding. And it's strong enough that we can see visible effects of hydrogen bonding. But that strength is nothing compared to the strength of the OH bonds in the individual molecules. So we have three types of intermolecular forces. London or dispersion forces are present in all substances. Then we have dipole-dipole forces. These are present in polar molecular substances. And then we can have hydrogen bonding, which is a very specific type of dipole-dipole interactions that can only involve either HF, HO, or HN bonds in atoms of different molecules. So water is probably the best example of hydrogen bonding, and we'll talk about that a little more. First, I want to talk about London dispersion forces. Every substance interacts with each other through London dispersion forces. These are weak, but they are significant enough that they can cause changes in boiling points. They can cause changes in phases. You may remember way back in the first lecture, we talked about how the halogen compounds, fluorine, chlorine, bromine, iodine, fluorine and chlorine are gases at room temperature, but bromine's a liquid and iodine is a solid. That is because of London forces. What happens with every atom is that at a given instant in time, the electron distribution within an atom may suddenly go uneven, because electrons are actually constantly popping in and out of existence. And on average, they'll be equally distributed around an atom, but in a given instant, there may be a temporary imbalance. Well, when a temporary imbalance occurs, that can induce a shift in electron density in a neighboring atom, and this creates an attractive force. So here in the cartoon in the upper right, we have an instantaneous shift in electron distribution. So an atom has a temporarily has a partial negative side and a partial positive side. Well, that induces a shift in electron density in a neighboring atom. So that a partial negative side becomes closer to the partial positive side in the first atom, and we end up with a little bit of interaction. Now, this becomes more significant in larger atoms and molecules. London dispersion forces are less in smaller atoms because it's tougher to get that uneven distribution. If an atom has a large number of electrons, it's easier to have an uneven distribution. It just takes 1 or 2 electrons to shift over to one side to create some attractive London forces. And so this is seeing in some trends. We've got the halogen series. Iodine is the largest atom. And fluorine's the smallest atom. Iodine exhibits a greater London forces, and so that's why it's actually a solid at room temperature. Bromine's a liquid. It has the next largest size. And then fluorine and chlorine, the smaller atoms, those are gases at room temperature. If you look at the noble gases in group 18 in the periodic table, helium, neon, argon, krypton, and xenon, even though they're very inert or unreactive chemically, they all have very different boiling points. And that's because of different degrees of London forces. Xenon atoms are the largest out of this group, and so it undergoes the greatest London dispersion forces, the greatest between one another. And so the xenon has the highest boiling point, or sorry, highest freezing point, takes more energy to melt it, whereas helium has the smallest atoms, fewer weakest London forces, and so it does not take as much energy to melt helium, so it has the lowest freezing point. So stronger interactions result in higher freezing and boiling temperatures. Weaker interactions involve lower freezing points, lower boiling points. So xenon, because of its largest size, has greater London forces, and so they interact more strongly with one another, leading to a higher freezing point than the other noble gases. So you can see here in this trend, we go helium, the smallest atom, all the way down the column to xenon being the largest atoms. And so the freezing points follow that trend. Now the next level of interaction are dipole-dipole interactions. And here, these can occur if a substance breaks down into polar molecules. So for example, we have acetone and chloroform, and both of these are polar molecules because of the CO bond in acetone, that's on the left, and then on the right is chloroform. The carbon-chlorine bonds are polar, the carbon-hydrogen bond is not, and so that gives a net dipole moment toward the chlorine side. And what will happen if you have a sample of acetone? Acetone's a liquid. It's used in fingernail polish remover. The acetone molecules will kind of interact and sort of line up in a direction. And it's not a rigid arrangement, but they'll sort of line up because the partial positive sides of the molecule will line up, will be attracted toward the partial negative sides of other molecules. So you'll have these interactions going on, and these dipole-dipole interactions are stronger than London forces. So again, keep in mind, London forces still exist in chloroform and acetone and all polar molecules. However, the dipole-dipole attractive forces are much stronger. The last type of interaction is hydrogen bonding, and these are very specific and stronger versions of dipole-dipole forces. So in order for hydrogen bonding to occur, you have to have molecules with NH, OH, or HF bonds. And so what will happen is that the hydrogen on one atom will be attracted to either the nitrogen, oxygen, or fluorine on another atom. And so here in the cartoons, we've got ammonia molecules in the left, hydrogen bonding. The hydrogen atom, shown in red, from one ammonia molecule is attracted toward the nitrogen on another. Water hydrogen bonds, so in the middle, the hydrogen atom on a water molecule is attracted toward the oxygen atom in another one, and then hydrogen fluoride also exhibits hydrogen bonding in the same way. And so these are attractive forces that help kind of keep molecules attracted together. And in fact, in a glass of water, you have a very complex system of hydrogen bonding going on. The water molecules are still flowing over one another, but every atom is involved in some type of hydrogen bonding interaction with hydrogen atoms or oxygen atoms on neighboring water molecules, and it can become very complex. Now, hydrogen bonding can have a big effect on properties like melting points and boiling points, and can show you here in a series. If we take water and compare it to all the analogous compounds where we have nonmetal elements from the same group, so this group 16 of water. So we compare H2O, H2S, hydrogen sulfide, H2SE, hydrogen selenide, and H2TE. We actually see two different trends in boiling points. So sulfur, selenium, and tellurium, they're all in the same group as water. So they will form compounds with hydrogen that have the same structure as water does. Now, if you look at those other three compounds, the boiling points increase as we go from H2S to H2SE to H2TE. Now, tellurium is the biggest atom in the series, and sulfur is the smallest out of those three. And so you notice as the boiling point is the highest for H2TE and the lowest for H2S, we can say that those three compounds interact primarily through London forces. And so with London forces, the larger the mass, the higher the boiling point, higher the melting points, okay? So if we were to take those three compounds and extrapolate what we should see for water, well, it looks like water should have a boiling point of about minus 80 or minus 90 degrees Celsius, but it doesn't. Water has a much, much higher boiling point than any of those other three compounds, and that's because water undergoes hydrogen bonding, which is much, much stronger than London forces. And so it is much more difficult to boil water than it is to boil those other three compounds. And so it's the hydrogen bonding property that causes the break in that trend. Hydrogen bonding results in a lot of interesting effects. I've already talked about one, how water tries to climb the walls of graduated cylinders and test tubes because of interactions between the water and the silicon dioxide in the glass. It creates what we call a surface tension, that at the surface of water, there's some resistance. The hydrogen bonding is more concentrated there, and so you actually have to apply a pressure to break through that surface of water. Now, it's easy for us to do. We have a lot of strength to do that. However, certain bugs do not. And so certain bugs and insects can appear to walk on water, and they're being supported by that surface tension. Protein conformations depend very much on the amount of water present, because that governs whether hydrogen bonding creates beta sheets or alpha helices. And this type of thing is very important in a lot of metabolic pathways, biochemical mechanisms, drug absorption properties. And so there's a lot of hydrogen bonding that occur within protein chains that are very important for our well-being. So I'll back to a couple of quiz questions maybe. Again, if we're thinking about quizzes, you could ask students which molecule is capable of forming stronger intermolecular forces. And the answer between nitrogen and water, the answer would be water, because water is capable of hydrogen bonding. Nitrogen, being a completely symmetric molecule, no polar bonds, can only exhibit London forces. Another question. Ethanol and dimethyl ether. And so we've got these structures below. You notice they both have the same molecular mass. They're composed of the same atoms, just different arrangements. Would one compound have a higher boiling point than the other? And why? Well, the key feature to look at is the OH bond on the ethanol molecule. That's something different. The dimethyl ether molecule does not have that OH bond. And as a result, the ethanol molecules can hydrogen bond with each other, whereas dimethyl ether cannot. And so as a result, ethanol has a much higher boiling point, 78.4 degrees, than dimethyl ether, which boils at minus 24. Lastly, we'll wrap up with one more quiz question. Consider the following compounds: ammonia, methane, and hydrogen. How many of the compounds above exhibit London dispersion forces? You might be tempted to say one or two. Actually, hydrogen and methane are both nonpolar compounds. However, remember that all compounds exhibit London dispersion forces. However, it turns out that ammonia also exhibits hydrogen bonding because of the NH bonds, and that hydrogen bonding is just a lot stronger than the London forces, so the London forces kind of get washed out, but they still exist. So that's it for intermolecular forces, and we'll see you in the next video.